In this section, we're going to talk about integrals that involve hyperbolic functions. So I'll start you out with the first one here. The hyperbolic cosine of u du is actually the hyperbolic sine of u plus a constant. So start you out with something simple here. So that means the hyperbolic cosine of x dx would equal simply the hyperbolic sine of x plus a constant. And then the next formula is that the hyperbolic sine of u du would be the hyperbolic cosine of u plus a constant. Now here I'm integrating 2x times the hyperbolic sine of x squared dx. Now what I could do here on this one is, if you let u equal x squared, then that would give me hyperbolic sine of u in the integral, and then du would actually be the derivative of u, which is 2x times dx. So it looks like that works out perfectly, because when you put the 2x together with the dx, that's your du. So this is really just the integral of the hyperbolic sine of u du, which integrates to the hyperbolic cosine of u plus a constant. So that one works out pretty good. On the next couple, I'll go ahead and use the u substitution with more emphasis. So in this one, if we integrate hyperbolic secant squared of u du, we get hyperbolic tangent of u plus a constant. So here you can see in this integral I have hyperbolic secant squared of x cubed. So I could let u be x cubed, so that would be the hyperbolic secant squared of u. But if u is x cubed, then du would have to be 3x squared dx. So the problem that I run into here is I don't have the 3 in the integral. I have the x squared dx, but not the 3. So I can just multiply inside the integral by 3, as long as I multiply by 1/3 on the outside. Now if you put the 3x squared and the dx together, that forms the du. So I've got the du, and then this secant, hyperbolic secant squared of x cubed, is the same as hyperbolic secant squared of u. So now I've got it in the form where I can use this formula, and so when I integrate the hyperbolic secant squared of u, I get hyperbolic tangent u times 1/3. Remember, I had to put 1/3 on the outside of the integral, and then plus a constant, and then at the end make sure you replace u with our substitution x cubed. So we just get 1/3 hyperbolic tangent of x cubed plus a constant. The next formula I want to look at is, if you integrate the hyperbolic cosecant squared of u, you actually get minus the hyperbolic cotangent of u. So on this one, I've given you an integral that has the hyperbolic cosecant squared of an argument here, and that argument is e to the 5x. Now, so if I want to use this formula, the u would have to be the e to the 5x. So I'll set that equal to u, and then when I take the derivative of it to get du, I'll get that du is 5e to the 5x dx. Well, again, I have e to the 5x and I have the dx, but I don't have the 5. So I can multiply the inside by 5, and then that way I have 5e to the 5x dx, which forms the du. But if I multiply the inside by 5, remember I have to multiply the outside by 1/5. And then so I've got the du, so I bring my 1/5 over, and then I know the 5e to the 5x dx is the du, and then this part right here is just the hyperbolic cosecant squared of u. So now I've got this integral into this form over here, and when I integrate that integral, I actually get minus the hyperbolic cotangent of u times negative 1/5. Well, the negative comes from the formula, because when you integrate this formula, you actually get a minus hyperbolic cotangent of u. So I put the negative there with the 1/5. And of course I had the 1/5 carry over from up here. And then the last step is to replace u with the substitution I used, which was e to the 5x. So I have, final answer is minus 1/5 hyperbolic cotangent of e to the 5x plus a constant. And the next formula is if you integrate the hyperbolic secant of u times hyperbolic tangent of u, it integrates to minus hyperbolic secant of u plus a constant. So up here you'll notice I have in the numerator I have hyperbolic secant of natural log of t, hyperbolic tangent natural log of t, and in the denominator I have t. And I switched to t here just to show you that we don't always have to have these integrals in terms of the variable x. So now let's see. I see a hyperbolic secant times a hyperbolic tangent, so it makes me think of this formula here. So if I'm going to use that formula, then the u would have to be the arguments of these functions, which is natural log of t. So the u would be natural log of t, and then du would be the derivative of that times dt, which would be 1 over t dt. Okay, now I'm going to rewrite this just so to make it easier for you to see how this works. So I'm just going to write the numerator here, and then instead of writing that all over t, I'm going to pull the 1 over t over here and multiply it by dt. That way you can see that 1 over t dt is the du that I've stated right here. So the 1 over t dt, that's just the du, so there's the du, and then this hyperbolic secant natural log of t times hyperbolic tangent natural log of t, that's actually just hyperbolic secant of u times hyperbolic tangent u. So now I've got it into the proper form where I can use this formula over here, and then when I apply the formula I get minus the hyperbolic secant of u plus a constant, and then the last step, replace the u with the substitution I used, which is natural log of t, not x. So I knew I would mess that up. When I change variables, sometimes I forget. So it's actually the hyperbolic secant of natural log of t plus a constant. Okay, there's one other formula. We have hyperbolic cosecant of u times hyperbolic cotangent of u du, and that integrates to minus hyperbolic cosecant of u plus a constant. Well, so here I've given you the hyperbolic cosecant of sine theta plus the hyperbolic cotangent of sine theta, and then notice I have a cosine theta d theta out here. Okay, well I'm just going to let u be sine theta, and then du is cosine theta d theta. So you'll notice I made this one work out pretty nice. This right here, this cosine theta d theta, that's actually going to be my du, and then here, since I let u be sine theta, this is going to be hyperbolic cosecant of u times hyperbolic cotangent of u, and then I just apply the formula, and that's going to be minus the hyperbolic cosecant of u plus a constant, and then replace u with sine theta, and I get minus hyperbolic cosecant of sine theta plus a constant. Now, there are formulas for other hyperbolics, like for instance here, this gave you the formula for integrating hyperbolic cosine of u, this gave you for integrating hyperbolic sine of u, and these other formulas actually come from the fact that you know the derivative of hyperbolic tangent of u is hyperbolic secant squared of u, or that you know the derivative of hyperbolic cotangent of u is minus hyperbolic, the derivative of that's minus hyperbolic cosecant squared of u. So these formulas actually come from what you know about derivatives involving hyperbolic functions. But there are, in case you're wondering, there are functions like, for instance, if you wanted a formula for hyperbolic tangent, there is one, and I can dig it up for you. So like I said, there are formulas for integrating the other hyperbolic functions if you want to look them up. And so for instance, if you want to integrate the hyperbolic tangent of u du, it actually integrates to natural log of the hyperbolic cosine of u plus a constant. Now that might be, let's see if that is, that's actually, yeah, that's, I thought that might be absolute value, but it's actually not. It's just natural log. And so you can see here there's formulas for each one of these 6 hyperbolic functions there if you were interested in looking at them. I just searched online for the formulas and got a set of all the formulas. Of course, you have to trust them, so you might want to, just like a journalist, find you a second source just to make sure that there's not any typos in these formulas. Okay, so that takes care of that. Now the next set of integrals I'm going to do involve integrating functions related to the inverse hyperbolic functions.